Today's lesson is on modeling with trigonometric functions, and it's one of my all-time favorite lessons. And not because of the examples that are actually done in this section, but to what they lead to. These modeling situations for trigonometric functions leads to sound waves, light waves, any kind of electromagnetic waves, electron waves. These are the beginning of really understanding the equations of anything that shows wave behavior. So we do some very simple examples here, but I don't want you to be underwhelmed by the possibilities here. These opening examples are just meant to be very familiar and get you used to how these equations can be used to model real life situations. So we start off with a very simple one. A point on the ocean rises and falls as the waves pass. If you want to visualize it, you can picture like a bird, like a duck or something like that, sitting in the ocean, and the waves are going up and down, and this duck is moving up and down with the waves as they go past. Now, suppose that a wave passes every 4 seconds, and the height of each wave from the crest to trough is 0.5 meters, so some fairly big waves here. Sketch a graph to model the height of the point relative to the average height for a complete cycle starting at the crest of the wave. A few notes here about what's going on. It says relative to the average height, which means the height of the ocean is, or of a lake, is very, 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 very deep. And so we wouldn't want to try to graph the height of the ocean. So what we're going to do is we're going to graph this thing relative to its average height, which is sort of relative to the middle. What that means is this duck is only going, it says the height of the wave from crest to trough is 0.5. That means it's only going a total of 0.5. It's going like 0.25 up and 0.25 down. So let me put that right on my scale to begin with, is that this thing's just going to go 0.25 up and then 0.25 down. And I don't want you to think that the height of the duck is ever at negative 0.25 because, it is, but it's only relative to where it would be sitting if there was no waves going by, relative to the middle. And that relative to the average height gave us permission to do that. In fact, it told us to do that. Next, switch over to a pen I like here. It says the wave passes every 4 seconds. So what we've got to do is we've got to have a scale that goes 1, 2, 3, 4 seconds. And we've got to do a complete cycle every 4 seconds. The other thing it mentioned was start at the crest of a wave. And a crest is the top of the wave, if you haven't heard that word before. So crest, I would switch to a color for graphing here. We're going to start at the crest of the wave. And apparently at 4 seconds, we'll have done a full cycle and ended up back at the top again. Well, this fills in the rest of it fairly easily in that if it's going to take 4 seconds to do a full cycle, that means it's 2 seconds before it gets to its trough. If you haven't heard that word before, trough is the bottom of the wave. And then you can even fill in the middles. Halfway between the high and low is the middle. And halfway between the low and the high is the middle. And it doesn't take long before I've got my nice graph here of one cycle. Well, let's just see if I've included everything in here. Sketch a graph to model the height of the point relative to its average height for a complete cycle starting at the crest of wave. Well, you might want some titles on here. I mean, you might say height here. And you might want time in, seconds? Okay, so there's sketching the graph. You just have to read the situation, try and follow through what's happening, and get your, basically I had to get the amplitude, the period, and where it starts. Those are the important things there. And what's nice about the graph is once you have the graph, making the equation is pretty straightforward. So I always suggest if you're having trouble in a question, try and draw a little sketch of the graph first because it'll help with the equation. And lo and behold, this question immediately asks for the equation of the situation. I'm going to try and zoom in just right so I can see both at once. Now, just like taking the equation and making a graph, when taking the graph and finding the equation, I think you take some notes here and you go, okay, well, what's the amplitude here? And I can see the amplitude here is 0.25 because it's going 0.25 up and 0.25 down. What's the period here? The period was 4 seconds. And what's nice about that formula I gave you is I can immediately use that formula to go, okay, well, K is 2 pi over the, rearrange that, right? K is the period divided by 2 pi. Let me show you where I'm getting that from, because I've rearranged that wrong, and I want to show you where it's coming from. So I gave you that formula. Period equals 2 pi divided by the k value. If I want to rearrange that, I get kp equals 2 pi, and so that's where I'm getting this k value from, which is 2 pi divided by the period. I had it the wrong way around there. 2 pi divided by the period here, which is 4, so I get a k of pi over 2. Now I'm in great shape to make my equation. You've got a major decision to make here, is whether to use sine or cos. And unless it indicates otherwise, I say use the most convenient one. On the next example, I'll show you how to use whichever one's inconvenient if it happens to ask you for the other one. But in this one, I'll just use the convenient version. And the convenient version here is definitely cosine, because cosine starts at the crest. We've got that word available to us. We were calling that the top of the wave, but it starts at the crest of the wave here. So if I use cosine, I put my amplitude there. The nice thing about using cosine here is there's going to be no phase shift. It starts right at the top nicely. Also, because we're doing relative to average height, there's no vertical translation here. So all I need is the k value, which is pi over 2, and I'm going to use t for time. There's my equation of the situation. It has the right amplitude, the right period. There was no phase shift or vertical translation. If you're right with the stuff from yesterday, if you had no trouble turning equations into graphs, that's not too big of a leap. You got to draw the graph and then think through what the amplitude or period are. The only important part is this choice between cosine and sine, and more about that in the second example. Second example: the water depth in a harbor is 21 meters at high tide and 11 meters at low tide. One cycle is completed approximately every 12 hours. Find the equation of the water depth as a function of time. Now it says find an equation here, but I've put some graph paper right here on the screen, because I need to tell you that doing these, going right to the equation, it is possible to be that good where you could just jump in and get the equation. But most times you're going to want some kind of sketch of the graph to pick off these features. Let's see, it's got to go 12 hours. So do I have enough room to do every second square? I don't want to jam things in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, I do. So I'm going to call that time in hours. Hours. There we go. And now meters. Well, I don't want to write on every line here, so I'm going to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. You don't need as good a graph as I'm building here to come up with the equation usually. A little sketch on lined paper is more than enough. I mean, sometimes we say, oh, you have to graph on graph paper. Well, yeah, that's true, but if you're just trying to get some features off a graph, you probably don't need that. But anyways, I'm doing a very good one here to show off that. Now, so I know the amplitude, I know the high and the low, and I know the period, which is one cycle is completed every 12 hours. But the question is where to start. Oh, it does tell me, after low tide. So it says start at low tide. Low tide being, let me switch colors here. We'll go with a nice blue for water, right? Tides here. Start at 11 meters. And you can handle this any way you want. Me personally, if I'm starting at low tide at 11 meters, I immediately jump to the end. I get that last point. It really helps me to visualize what's happening. And it said 12 hours for a complete cycle. So after 12 hours, apparently, we'll be back at height of 11 again. Did I get that right? The lines are messing me up here. Okay, yeah, good. And then I can go to the middle. That's where I go, is to the middle. So then at 6 hours, it's going to be at its high point. 6 hours at its high point. And that means it's 3 hours, it's going to be in the middle. Halfway between 11 and 21 would be 16. So there, I've got that. And then at 9 hours, I got 16 as well. I really like getting those key points on there because it helps me draw the graph. And I do that by just going halfway. I do the full period, then I do half the period, and then these 2 quarter period marks. Those are the key points for sine and cos that we saw before. And then a nice Smooth curve. Now, one little thing that's going to help, just a little tip. As soon as you draw a graph like that, I suggest you immediately draw on the axes. And the axis is this vertical line that sort of cuts this in half. And I'm going to draw that right on there at h equals 16. That's my key trick for the day, is to put that on there because it's really going to help in everything we're going to do. And you'll see why in just a second. So, ready to do this equation. The equation of the situation, I got to choose between sine or cos. And in this particular example, I'm going to do both sine and cos in just a minute, but I'll start with the more convenient one, the one you'd probably choose if you had your choice here. To me, this looks like a cosine graph. And the reason it looks like a cosine graph is because it starts at one of its extremes. It starts at the crest or trough. I know cosine normally starts at the crest. I get it. But this one starts at the trough, and that makes one little easy adjustment to make the equation. There's many choices here, by the way. There's many right answers here. But the most convenient one to me would be to go, okay, h at t will be equal to negative. And what I've done, and I've put a negative right out front there, is I've done that vertical reflection. And what that allows me to do is start at a trough for cosine. So when you want to start at a trough, I suggest negative cosine. Then the amplitude. Okay, well, putting this axis on here, h equals 16, helps to find the amplitude because I know that the bottom was at 11, the axis is at 16, that means the amplitude was 5. There's fancy formulas out there for it to find amplitude. You can do something like max minus min divided by 2, and that's fine. I don't mind those formulas at all, and they can be useful in certain situations, but they become a memorization problem when you're first learning about these things. And I like the idea of just putting the axis on there and just looking and finding what the amplitude is, because it's laying right there. It's the distance between the middle and the extreme, whether it's to the crest or the trough. Oh, and what did I decide here? It seems like a long time ago. Cosine. That's what I decided there. Whereas up here, this one I did cosine as well. I'm going to show how to switch over to sine in just a second. Negative 5 cosine. Now, the period is 12, so just a few notes over here. I'm going to go back to my formula. Period equals 2 pi over k, which means k is 2 pi over the period. So I get a k value of 2 pi over 12. My k value for inside the brackets this time is pi over 6. Because I've cleverly chosen cosine for my graph, I have no phase shift, but there is a vertical translation. But the nice thing is, when you've got the axis on here, the axis is the vertical translation. That confuses people sometimes when they first see it. Normally, cosine has its axis, its middle at 0. So wherever its axis moves to, that's what the vertical translation is. You might look at this and think the vertical translation is 21, or maybe it's 11, but you really have to look at where the middle went. And the middle of cosine is normally at 0. The middle of this one is at 16, so this has been moved up 16. You can punch that into Desmos to double check that it gives you the graph you want. Very nice move. On a test or something like that, you could sub in a couple of t values, like t equals 0, t equals 6, and make sure this equation gives you exactly what you want. The only thing remaining is to talk about how to deal with sine. And that's a little bit difficult. There's some things that don't change when I go to a sine equation for this graph. Is it would still have the same amplitude. It would still have the same k value. But it might have a phase shift, so I'll get ready for that. And it would still have the same vertical translation. So that's all fine and good. After that, I only have to decide on what I'm going to use, as far as I can use a vertical reflection, or I can just use a phase shift. I don't use vertical reflections when I'm switching from one graph to the other unless I absolutely have to. I just do this trick here. Here's what I do. I think in my brain. I go, where does sine normally start? And sine normally starts in the middle on the way to a crest, on its way up. Here it is right here. I just grab my highlighter and I go, there's sine right there. There's where sine is actually starting in here. And someone's moved it to the right here because the start value on its way up has been moved right 3. And that's all I need. Once I get that far in my thinking, I'm home free and I can get that phase shift. The phase shift is right 3. So I'm putting a minus 3 in there. Okay, so find that cycle that you want. the opening cycle of sine. And the opening cycle of sine starts in the middle on its way up. Now, I don't want you to think for a second, again, I mentioned at the start, I don't want you to think that the modeling for trigonometric functions is all about tides, which it is. You can model tides using sine and cosine, absolutely, and they do all the time. And that's how they make the predictions of when high and low tide are going to come in at ocean, on coastal areas. But there's more to it. I'm telling you, this is really, really going somewhere big in physics and engineering and chemistry. So don't underestimate what I've given you here. Take a run at this homework. This chapter's wrapping up. We got one more section because we'll touch on maybe rate of change, but we won't do too much with rate of change, or we might not do any rate of change at all for this section. So we got maybe one more section to look at, and then this chapter wraps up. So